we saw that really a central paradigm of the linear time approach to verification, to model checking, is that we express verification condition at the end as a containment problem. So you can also think of it as in some sense, this is, you can think that this is even more fundamental than automata. This is, the idea is the verification is a language containment. Language containment approach. From this point of view, it doesn't almost matter whether this is the implementation and this is the specification, and you're checking for containment from above, or if this is the implementation and you want to make sure that some behavior must be there in the implementation, which will be verification from below. Okay? This is really what verification is about. It's a containment relationship. And when you look at it from this point of view, and it kind of intentionally has become more symmetrical, you realize that some of the rhetoric of the initial idea of people, if you go back to Tony Hoare's 1969 paper, which is an incredible axiomatic basis for computer programming, which kind of put forward in a very, this is the beginning of what we call Hoare semantics. And he says, well, once we verify the program and the compiler and the hardware, then we will know that our systems are correct, and we'll have mathematical certainty that our systems are correct. And this is, I think, was somewhat, it was early, I mean, 1969, almost 50 years ago, and somewhat naive, because all you can do is you can compare two things. This is, let's say, this is a specification. There may be errors here. How do we know that there are no errors here? All you can do, really, ultimately, what we do in all the attempt to verify, to validate, to increase reliability of programs, we can look at the same object using different glasses and see what we are seeing is consistent across. And inconsistencies tell us there's something wrong with our thinking. The requirements we wrote formally maybe did not capture our intuition properly. We made a mistake in design. All you can hope is to catch inconsistency. Okay? There's really no mathematical certainty in correctness, because correctness is always relative to what you intended, and what you intended is always a fuzzy object because it's in your head. And so this is the one important thing that we saw. The second important thing that you saw is that this on the face of it is difficult because there is a universal quantifier here, right? It's everything here is here. That's difficult to check because you are quantifying over an infinite spaces. We are looking at even omega words. There are uncountably many omega words. So we'd like to reduce it to an existential quantifier, which is more constructive. And we reduce this to A1 cross A2 bar. And we want to check for emptiness. In fact, we look at the dual. Okay, we look at the dual, we check for non-emptiness, and now we're looking for a witness. And we say, so what is the complexity? We saw the complexity is linear time in A1 and exponential in A2, and we said this is okay if A1 is the implementation, it's large, and A2 is the specification, it is small. But now it's too bad that I want to add one more thing, which is the parameterized complexity approach to that. So if you look at the analogy to what we heard from Stefan, what can we take here as a parameter? A2. We can think of A2 as a parameter, or the size of A2. So let's suppose that this is of size n, and this is of size k. Then we know that once you construct the graph, this is a linear time problem, linear time in the sense of complexity theory. You can do graph reachability or even lasso finding in linear time. And so we saw that the complexity is going to be O or 2 to the O of k times n. And what would Stefan call this? No, there is a term for it. Use 3 letters. FPT, this is fixed parameter tractable. So it's not only that because it could have been, for example, yeah, it should be KLOK. Yeah, close enough, thank you. But it could have been, for example, something like n to the k. And I could still try to argue, oh, it's okay, k is not that small that we would be happy to take it as in the exponent for n, because n is very large. So it's actually this is really what he was trying to tell us, I think, in the very first lecture. The automata-theoretic approach gives us typically fixed parameter tractability result, where the blow-up is in a construction of the automaton. But once you do that, you have a separation, because you're just taking a product, and we saw that the product is a fairly simple operation. And so we get, on top of not only we're getting that's linear in the system and exponential in the specification, but in addition we have fixed parameter tractability. Okay? And this is something you always get from the automata-theoretic approach. You get this separation. And you get, in fact, typically you get linear time result. Any questions about that before I move to the next topic, which is bringing logic? Until now we had no logic, just automata. Any questions? Anybody here speaks Mandarin? Can you say in Mandarin 44 stone lions? 44 stone lions. 44 stone. No, don't tell him what to say. I want him to say it in Mandarin. Do you understand English? How do you say it in Mandarin? I love it. I love it. Told you. You can never say it properly. Only somebody who really speaks Mandarin can say it properly, because it's the same sound, but it's pronounced about 7 different ways. Thank you very much. You made my day. Okay, logic. So we said that we want to describe words using logic, and that means that we need to take a word such as abracadabra, and said we want this to describe as a logical structure. And the logical structure, to remind you, we say logical structure has to have some structure or a model. We'll call it, has domain, and some relations, and some functions. In fact, here we will not have functions. So how do you describe a word as a mathematical structure? So there is a natural approach that one takes. You say, look, there are positions here. Okay? I will take the positions as my domain. So I would say this is a word of length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the domain here would be D, would be 0 to 10. The length of the word. And what should we need, there is some order, right? We have a natural order that we go from left to right, or in Hebrew from right to left. So there is some languages from, top down. I don't know if any language goes bottom up. But there is an order. So we're going to have an order relation. And finally, we need to know at which position what letter is written. So if we have an alphabet sigma, we will introduce a monadic predicate P sub A for every A in sigma. And the intuition is that P sub A of I is true. It means that in position I, the letter A is in position I. And these ideas arose independently. It's one of these strange things. That's an idea pops out, and several people have it at the same time. And this idea pops around 1957, independently in the United States and in Novosibirsk in the Soviet Union. So just one of these cosmic confluences. The idea was in the air. So let's see an example. Suppose I write the following. There exists x such that for all y, y is less than x, and p0 of x. What does it say? No, you. Right, the final y final, because this is a point x such that everything is less than x, so this must be the rightmost point. And at that point, you see 0. So the last character is 0. Okay? And we saw, remember, one of the things we saw automata that capture the same thing, the kind of automata, and we'll talk about the last thing. And the theorem that is called the Bushi-Elgot-Trachtenbrot theorem relates automata and logic in the following way. I think that's when the papers came about. No. Bushi-Elgot-Trachtenbrot is on finite words. It's in 57, 58. And then Bushi is the extension to infinite words. I'll talk about it. Yes, Bushi also. This is the other Bushi was when I talked about Bushi, and this was Omega Automata. This is 1960. But the early version, which is just finite word, which is done by Bushi, Elgot, and Trachtenbrot, is 57, 58. He was actually in the US. Yes, he was in the US, yeah. Here's another, I mentioned to you before about how Schwecker was mystified how in 1985 he suddenly became very, very popular. The other side of the story, I never met Bushi. I think he died around 85. But what I'm told by people, one, he was a difficult man, and he always felt underappreciated. And I always felt that the final injustice, but I'm sure when he sat in heaven, he complained to God, he says, finally Bushi automata are getting popular, and you kill me just before I get to that point. So what we saw is given an automaton, we talk about the language of the automaton. If we talk about a first order sentence phi over the vocabulary, remember what is the vocabulary now? Vocabulary with the signature is going to be the order relation and these monadic predicates. So given a sentence, what typically we associate with a sentence? A set of given a sentence, it has what are the major branches of mathematical logic? Anybody knows? Proof theory? Model, thank you very much. Given a sentence phi, we have models of phi. And models of phi is a language now. This is a set of words. So a logic now has some expressive power. It describes some set of collection of a family of languages. So let's stay for a minute among finite words. So we know that if we're dealing with DFA or NFA, the set of all languages that can define, that's what we call regular languages. So now let's say given first order logic, okay, we can ask, what is the expressive power of first order logic relative to, let's say, to finite set automata? What can first order logic define? And the answer is that first order logic define less than automata. And there's something that you cannot express in first order logic. What is you cannot express in first order logic? For example, let me ask you, the set of all words of even length, is this a regular language? Why? The trivial automaton, right? Two states, just flips between two states. It counts modulo 2. First order logic cannot count. So if you just look at first order logic, it's too weak. You very quickly see that you can prove that you cannot count, and therefore you cannot express regular languages. And therefore people look, okay, we need to go beyond first order logic if we want to really capture this. And it turned out that you need a fairly minimal extension. You need to be able to quantify over sets of positions. And what do we call quantification over sets of positions? Monadic. So we talked about MSO. We talked about monadic second order logic. And in monadic second order logic, as I was saying, we can count modulo 2. How would we count modulo 2 in monadic second order logic? Suppose you can quantify over sets of points. How would you count modulo 2? You say, let's say there's a set of even points. There is a set P, which you think of it should be even. And now you need to say at the leftmost point, the leftmost element is not in P. And then you always go from P to not P and vice versa. And the last point is in P. And it should be fairly easy for you. Hopefully you can see it's an easy exercise to write it all in first order logic, all these conditions. And therefore I can say the word is of even length. And so now, okay, we've done one example. Is it true in general? And this is the beautiful theorems of Bushy, Elgot, and Trachtenbrot. Bushy, Elgot, and Trachtenbrot. And Trachtenbrot lived very long life. He died just a couple of years ago. Last year or 2 years, not more than that. And Trachtenbrot was in Novosibirsk. Bushy and Elgot were both in the United States, somewhere in the Midwest. And the interesting story is that I never found all the details. At the time, if you want to announce the result, before you publish a paper, you want to announce it. And there was you couldn't have a quick publication conference, and you couldn't put it on archive. So there was something called notices. Notice of the American Mathematical Society, and you basically send an abstract, which was unreferred. It was just published there. It was just a way to claim priority. So Bushy and Elgot submitted together an abstract, and then they went on to publish separate journal papers. And I've tried to find out what really happened there, and nobody could tell me other than Bushy was a very difficult man. So what is the theorem? This is the Bushy-Elgot-Trachtenbrot theorem. And the theorem is that MSO is equivalent in expressive power to, let's say, DFA. And really, I consider this one of the most elegant theorem that I know in mathematical logic, because the way it relates things that are so different in nature, okay? So logic is this high-level, expressive, it's kind of, if you look what it's, it was meant to capture the human mind, so to speak. When Boole wrote his treatise in 1847, he said the goal of this treatise is to capture the laws of the mind. This is how people thought of what logic is. And then you have these automata, which are just the lowest level, go from this state to this state to this state. And here we have this beautiful connection between them. And this happened just independently. These people probably know little about computing. They probably at this point did not hear about compilers. And we have the same idea that we want to bridge high-level languages with low-level languages. Now, how does one prove a theorem like that? The proof turns out is constructive. You actually go from one direction to the other. So one direction, and here of course I can say equally well NFL, right? One direction, if I'm given an NFL, it says A I have to map it to some sentence phi sub a that would capture it. This is actually not a difficult exercise, so I'm not going to go through this explicitly, but let's just have some idea. How would we, remember, what does NFAA say? There is an accepting run, right? There is an accepting run. How do I encode the existing accepting run in MSO? So if I don't even care about being efficient, I'll introduce a monadic predicate for each state. I mean, I can do it if you can see it, I can do it with log n predicates. But if I don't care about it, if there are n states or k states, I will use k predicate, and I will say there are monadic predicates, and these are the states. And I will say in every point only one of these predicates is true, and now I need to say that they obey the transition relation, and this is all going to be done in first order logic. So this is really an easy exercise. I'm not going to go through this, okay? And you can see also that this is a linear time translation. The blow-up is basically the size of your sentence is going to be roughly the size of your automaton, pretty much, so modulo encoding. The other direction is how to go from a sentence, from an MSO sentence phi, map it to an automaton A sub phi. This is really the non-trivial part. And as we're going to go later to omega on infinite words, where we again have the theorem, then it will only be Bushy's theorem, then it's more difficult. This is the direction that's more difficult. That direction is always easy exercise. Because on the face of it, the logic seems more powerful than automaton. So how would you try to prove generally, if you try to prove something about the sentence phi, what's the obvious approach to take to logic, to try to prove things for logic? Induction. When you see logic, first thing you try to do is you do induction. In fact, one of the things when I teach a course on logic is to, usually induction works, but sometimes it doesn't. For example, you cannot define satisfiability by induction on the structure of the formula, right? You cannot do that. If we do it, it would be easy, but some properties are not inductive, but some are very amenable to induction. So we would do it by induction on the structure of the formula, okay? Now, there should be part that you should say is going to be very, very easy. Suppose, by induction, if I have to do it for phi 1 and phi 2, then you can see that conjunction corresponds to what automata-theoretic operation? Intersection. So you see that to do this, you just simply take A phi 1 intersection A phi 2, which we know how to do. And if you have to deal with negation, then this is complementation, and if it's DFA, it's trivial. If it's NFA, you have to do subset construction, you have to do it. So what's the difficult part? What do we have here in addition to the Boolean thing? We have quantifiers. And for simplicity, I would rather deal with first order and second order quantifiers. I will deal only with second order quantifiers, but I'll have two types of second order quantifiers. One will just say there exists some predicate P, and the other one will say there exists one P. The intention is that P is going to be a point predicate. It must be true only at a single point. And therefore, because it's true only at a single point, it corresponds to what? To a first order, to exist X. It's like just saying there exists an X, right? So I said there is a predicate that's true only in a given point. So this is the only, in some sense, non-trivial part. And it's partly non-trivial because in 1957, we don't have NFA. The only DFA is in 1957. But this was non-trivial then. But now we have NFA. So what does exist P mean? It means that you're looking at, you want to accept a word, there is some, and now a word what is the alphabet that we are dealing with? This is now logic, right? So we can think that the alphabet is going to be, essentially you have a set of, we can think of, you have a set of predicates, and the alphabet is something like 2 to the pred, right? Because at several predicates can be true in the same point. So we can encode our alphabet, again, by some logarithmic encoding. So you have several, there are several instances. You can think of every predicate is just a binary, it's a binary letter, and every letter will encode by some binary notation. So what is the operation that corresponds to exist P? What is the automata-theoretic operation that corresponds to exist P? So you should try to remember that regular languages are closed under Boolean operation, but they have other closure operations. For example, projection. What is projection? Projection is when you have more details and you want to map it down to a less detailed language. In particular, what happens here? We have a set of predicates that includes P, and we want to map it to 2 to the pred that is without P. Because we say, is there some P such that? So I have an automaton at this level. I already have an automaton that accepts something if P is written there, and P, for example, would denote the even and the odd points. And now I want to erase it, and I still want to check that this is accepted if there is a way to add P. So what would the automaton do to check that this, you could accept it if P were there? What should the automaton do to check it? Guess. Okay, this is the beauty of non-determinism. The automaton would simply guess, I'm going to go over the words, and I'm going to guess some P's. And non-determinism means that we take the best possible guess. This is the beauty of non-determinism. We take the best possible guess. Right? We say, is there some guess that will make this true? Which is exactly what we're asking. Is there some P, which is your way to assign P true and false at every point, that will make this true? So the automaton guesses the P and check whether, right? So we had exist P phi. This is psi. And we already built an automaton for A phi. So A psi, what does A psi have to do? A psi has to guess P's, simulate A sub phi, and check that it accepts. And all it has to do, there has to be one good guess, and this is good enough. And if this was, instead of exist P, if this was exist 1P, then what should A psi do? You have to check there is a guess P such that A phi would accept. And in addition, you have to check that there's some requirement on P, right? It has to be a point predicate. So it has to be true only at one point. So how can the automaton check that P is true only at one point? It needs one bit to remember, has it happened? And once it happened, it can never happen again, right? So you have to double the state space to remember, has it happened yet? And if it happens, you're done. And if it didn't happen, when you get to the end, it didn't happen, at this point you reject, because it has to happen exactly at one point. So all these are what I call very, very simple programming with automata. These are all very easy exercises. This is undergraduate level exercises. But one reason this is now undergraduate level exercises is because we have NFA, we have the power of non-determinism, so you should guess. But in 1957, they couldn't guess. So what we would do, now, we will not keep it in NFA. If we do that, even we will ultimately translate it to DFA. Why? Because we have to deal with another operation. Complementation, right? Complementation is going to be, so projection is easy for NFA. Complementation is easy for DFA. So today we says, well, do everything when it's easy. Do projection on NFA. You have to do complementation, then translate to DFA. In particular, if I have, what would I do about the universal quantifier? How would I handle, so NFA can handle very easily existential quantifiers. What about universal quantifier? You negate, exactly. You know that this is equivalent to naught E naught. So you negate, and which is easy for DFA. You project, you get NFA, you determinize, you get a DFA, you complement again. So if you go today and you look, so today in some sense when you have NFA and DFA, this is really an undergraduate level exercise. You can give it to, you have taught all the closure operation, and you can teach students, here is the logic, now prove the theorem, and freely go between NFAs and DFAs. And it's easy. In 57, they didn't have it yet, and that meant they had to do the projection and determinize it in one construction. So in some sense, even though we give credit to Rabin and Scott for introducing non-determinism and then showing that it's equivalent, really the subset construction really shows up first, not in the Rabin and Scott paper, but in the early paper, because that's what they had to do. They had to deal with, they had to do the guess and then do the subset construction on top of it. So that's where you see subset construction in the first time. So this is really essentially how the proof goes for automata on finite words. Any questions about that? I didn't go over the details because these are really, once you have your automata theory on or just standard NFA, you know that these are all, it's a very simple translation. Simple, but what is going to be the complexity of going from phi to A sub phi? What is the complexity? I want to translate from a sentence phi to an automaton A sub phi, and I do it by induction, right? And we know some of the operation, union should be easy, intersection should be easy, projection is easy, complementation is, bam, exponential. What happens when I have every alternation of quantifier give rise to another exponential factor? Okay? Because even remember that every universal has negations there. So what happened? We do this by induction, and every time we have a projection and we have to complement, we get another exponential factor, and the result is going to be, the final result is going to be if you're given an automaton of size, you start with a formula of size k, it will be, let me go of this height, probably some n, have to do with the size of the sentence. This is where we talked about non-elementary growth. Okay? Now, just so you'll get some ideas of what happened when these things blow up. So let's see, we have 2 equal 2, and 2 to the 2 is 4, and 2 to the 2 to the 2 is 16. And 2 to the 16 now is going to be, I think, no, not can be. That should be, 2 to the 10 is about a 10, so this should be about 4,000. That's it. The next level is already the end of the universe. No, 216? No, it should be more, should be more. 10 is 1,000 and 2 to the 6 is 32, 32,000. I think it's roughly, no? 2 to the 10 is about 1,000. And 2 to the, 64. Oh, well, 64. So we are done now. 2 to this number is the end of the universe, okay? So non-elementary is a horrible complexity. Now the interesting thing is, so on the face of it, if you just look at it from complex theoretic point of view, this is horrendous. Still FPT. Still FPT, but the complexity in the parameter is going to be non-elementary. Then, maybe about 10, 15 years ago, a bunch of people in Europe said, you know what? We're going to implement this. And people says, are you guys out of your mind? You know, just think about the energy that you're going to use, right? Will cause energy crisis, just trying to, the energy need to do that. But there is a software package called MONA. Short for monadic second order logic. And you can go and implement, you can go and use MONA and write on various sentences, and it's not the end of the universe. So how can it be? I mean, you think you'll hit enter and then your laptop will start smoking, right? But it doesn't typically happen. How can it be? We just talk about this horrible complexity. What is the essential assumption when we talk about complexity theory? What is the worst case complexity? Okay? Worst case is a very pessimistic approach to life. Okay? The worst case, horrible thing can happen in the worst case. Okay? Donald Trump planes would drop on the way to Poland and it would start a war between Poland and the United States. Okay? Mixed blessing, yes. So I wouldn't ask which part. So it turns out, yes, we can write sentences that are incredibly succinct way to describe very large numbers, essentially. And this is partly what also Stefan talked about. You can express numbers in a very, very succinct way. So we can be very, very, very clever and write sentences that have, the automaton will be incredibly large. And essentially we wrote very succinct way by kind of bootstrapping, writing something again and again and again to create these very, very long, essentially, structures. But normally, these kind of sentences are not the normal sentences that show up when we actually try to specify systems. Now, on top of it, Mona uses DFAs. So whenever it has NFA, it immediately determines. What do we know about, there is one very important fact about deterministic automata on finite worlds. One of the most fundamental theorems about this, about DFAs. If you minimize DFAs, you're nodding, yes. What happens when you minimize DFAs? All minimal DFA for the same language must be isomorphic. There is a canonic, call it canonicity. Once you minimize DFA, they're canonical. So that means that you don't have to worry, how did I get here? The answer is, if you're working with DFA and you minimize them, you're going to get essentially the same object. So Mona, when it does it by induction, it minimizes it at every step very, very aggressively. So it won't happen, because if you don't do that, you can think you might have a very large intermediate result, and then it will collapse when you minimize at the end. So it minimizes, at every step it minimizes. And then it uses a clever data structure to represent fairly large automata. It uses Boolean binary decision diagram to represent automata. So these are symbolic way to represent large structures. And as a result, you can handle actually fairly large automata there. Of course, there will be, it's easy, once you know what happens, you can give it some clever sentence that will just blow it out of the water. But in practice, actually, it works reasonably well. And I'm emphasizing it because I'll show you in a few minutes where this is not the case anymore. So this is all of this theory, as I said, this is late 50s, 1957, 58. Even though the implementation only happened in the, I think maybe started about 20 years ago, they started doing implementation. All of this work, we say 57, 58, but I told you that in 1960, Bushy said, what happened if we want to extend it to omega words? So what happened when we extend it to omega words? When you extend it to omega words, and the motivation came from church, from reasoning about sequential circuits. You still can do kind of the same proof, essentially. By the way, just one thing I forgot to add. What I gave you so far is a upper bound, right? There was just an upper bound. And you could ask, maybe you get this upper bound because you kind of did things stupidly by induction, and maybe there is a way to not to do it by induction and be more clever about it, which we'll see later. Sometimes it does work. In some other context, this not doing things by induction, it's a good idea. But here you can think maybe it just was a stupid way. So again, in 57, 58, people did not think about lower bounds. But if you go back about 17 years later, Stockmeyer does his PhD, and Stockmeyer proves in his PhD that you cannot do better than non-elementary. So these are one of the first, the kind of the worst lower bounds that we have, other than undecidability, something decidable, but has a very, very high complexity. And it was first shown by Stockmeyer in 74. So really, we know that you cannot do better in the worst case than non-elementary. So in 1960, Bushy wants to do the same thing. But he wants to do it for omega words, and he proved the same theorem now for omega words, that MSO is equivalent. Now, let's call it non-deterministic Bushy automata. Now we know there's no deterministic equivalent in Bushy automata. We'll come back later to other way. How do we determinize nevertheless? But that meant that he goes through the same proof. And again, what is the hard part here? What will be, projection is easy for non-deterministic automata. Union is easy. Intersection, we saw it's less trivial, but still you can do it. Wasn't too difficult to do, just with a little work. The hard part was you come to complementation. And it was hard because you could not determinize. You have to go from one deterministic automaton to a non-deterministic automaton for the complement. And this is hard, and we will see if I'll get maybe in the last, maybe tomorrow I can say a few words about some of the difficult construction and what are the basic idea underneath these constructions. But he gets the same result. But what do we lose by not having deterministic automata there? We said that DFA has very important property, which is used very aggressively by Mona. What was the property? Canonicity of deterministic automata. Now we don't have deterministic automata, and we don't have canonicity. So there is no treatment, there is no, even though we have the same theorem, we don't have omega Mona. Okay? We don't have the package that will do the kind of the same thing that was done for MS over finite words, for MS over infinite words, because the algorithmics is just much more difficult. Okay? And what's interesting is that, I would say, is the community essentially starting from the early 80s, for the following 30 years, focused very much on a lot of hard work, a lot of beautiful results about using about omega words. And only in the last few years, people say, you know what? This is just so hard. Let's see what we can do with finite words. Okay? And finite words are just much, much, much easier. Okay? So from the point of view, if you're interested in building a career and proving beautiful theorems, maybe it's more interesting to go to omega words. But if you want to build tools for people to do some reasoning, it's much, much easier to do it over finite words. And this is actually something that's very much active research area just in the last couple of years. Let's take now a 5-minute break, and then we'll continue. So now, to continue our story, we're going to go to New Zealand, to the southern, I think it's the southernmost university in the world. I think it's, yeah, I think so. I don't think there's anything else far south. It is Christchurch, New Zealand. And we find a philosopher called Arthur Norman Pryor. And he is a philosopher who thinks about, first of all, he's good, what's called analytical philosophy, which kind of means logic. Analytical philosophy is good training in logic. He writes textbooks in logic. And he's very interested also in ethics. And I think he writes a book about the logic of ethics and logic of ethics, other than the ethics of logic, the logic of ethics. And if you're interested in logic and ethics, you have there's one huge philosophical problem in the logic of ethics. What is the most fundamental philosophical problem in ethics? It's the questions of free will. Do we have free will? Ethics assume there is some concept of ethical responsibility and moral responsibility. But if we're just automata, if we look at a machine, you don't think about the ethics, is this an ethical machine? I mean, now we're building such a sophisticated machine and people are starting to talk about the ethics of robots, okay? But we don't talk about the ethics of this camera. You can do bad things with the camera, we don't blame the camera, right?
Yeah, when you see the videos, we'll talk again.
No, we blame the cameraman, not the camera, okay? So free will is the idea that we have agency, that we can choose, I can choose to do this or to do this, and that was my choice. And so Pryor wants to start to talk about these kind of things, to try to reason about free will. But free will has to be about choice, about actions, about consequences. And logic was kind of static at the time. Logic is static, it just talks about what is true and what is false. It wasn't clear how you use logic to talk about time. Time is an essential component when you reason about ethics because it had to do with actions and their consequences. So Pryor goes and invents something that we call temporal logic, which is the logic of time. And what is the logic of time? You start with static logic. And we are dealing here, there is a first order version, but we are going to speak all the time with propositional. Propositional temporal logic.
When is this?
This is early 50s. This is early 50s. This is early 50s. Early 50s, and he started thinking about it. There is actually a date. I think it was he died fairly young. I think he died in his 50s, and people do some interview with his wife, and she remembered distinctly when he invented it, because she already went to sleep, and he was still walking, and he woke her up, says, "I've invented a new logic, the logic of time." So she remembered. He was so excited he woke her up. Okay, I don't know if I. So, and the idea is a very, very simple idea. So let's imagine time, we get into kind of the same question, what is the structure of time? Remember I talked about linear time, about branching time, but he started thinking about linear time. And he said, let's assume that there is time 0, and then there is a discrete time, maybe we calculate seconds. If it's a computer, we have cycles. Our computers are typically synchronous. There is a clock, and there's a clock cycle. So there is a clear notion of this moment on time and the next moment of time, etc. And what do you have at each point in time? Each point of time, you have its propositional logic. So you have a set of propositions. And each element here is a truth assignment. So it's an element of 2 to the prop. So you can think now of a full description of logic in time the same way that one truth assignment described to us one time point. Now we say that a trace, if you want, is going to be an element of 2 to the prop to the omega. Just infinite omega sequence of time points. So you go again. This is assumed that this is unbounded. You go forever. So this is one trace, one behavior, if you want. But now we need to be able to talk not only about what is true now. You can talk about what is true now. Let's suppose that this is now. We are here. This is now. We want to say what will be true tomorrow. So we need for this, we need a temporal connective. We'll have a temporal connective for next. And by tradition, we use for this something that the X is for next time. Or sometimes you see there are two traditions. The other tradition uses circle, and it comes more from modal logic. And you want to say other things that you want to say is certain things are always true. And again, so always, again, for some reason, this becomes known as globally in time, and that's become the G or the box. Or you want to say sometimes in the future, and this is called eventually. And this usually people use F or diamond. And one way to remember the box and the diamond is the box is always stable, and the diamonds will eventually fall off. This is how you remember which one is which. And so now we can define it kind of a very rigorous semantics. So a trace tau satisfies a proposition if tau 0 satisfies the proposition. Proposition just talk about what is true now. And we have the usual semantics for conjunction, disjunction, negation. It's just the usual decomposition. But we need to define semantics for what does it mean for tau, for tau to satisfy next phi. Now we need to look at the suffix. Now we need to chop off the, so we can take any trace and delete the first point, and we get a new trace. And we can call it the successor of tau, if you want. And this is if the successor of tau satisfies phi, and tau satisfies f phi if some successor sup j of tau satisfies phi for some j greater or equal to 0. Just chop off enough, a finite number of points, and then phi will be true. Now, I don't need to write explicit definition for G, because we have, you can see that we have this thing that G is not F not. Something is always the case. If it is not the case, it is sometimes false. Something is always true. If it is not the case, it is sometimes false. So this is the temporal logic that Priors defines. Now we can ask, okay, this is temporal logic. We have this new logic. And a question is, what is the relationship between this proposition, this is what essentially is a propositional logic, and first order logic? So you can see that I could write everything. I could say, well, a trace is an omega word, and it's a structure, right? What is the domain of a structure like this now? What is the domain now of infinite word? It's instead of a finite set, a finite prefix of integer, it's instead of all the natural numbers. with the order between them. The same way that we went from a finite word to a logical mathematical structure, we can go from an omega word. Now the domain is simply the set of natural numbers. And we can have first order logic on traces. And you can see that this is very clearly, this is something that you can express in first order logic. Because you have to say this is true if phi is true in the successor point. And how do we have we have a linear order, but how do we capture successor here? If you have only order, how do you capture the successor? Has to be something that's larger, and there's nothing in between. So you can, first order logic, you can, even if I just give you order, you can capture successors. So you can see that to say that something is true in the next state, this is expressible in first order logic. And what about something like f phi? Something will be true at some point in the future. There is some point which is a larger point. There is a point which is larger than the current point, and phi is true there. So there is a translation. There is a translation from, this is also called linear temporal logic, because this is a logic on traces. There is a translation from LTL to first order logic, which is very easy. It's an easy exercise. You can basically take everything I've done here, and you can go and very easily translate it to first order logic. Now the question is what about a translation in the other direction? But Prior doesn't really ask this question. He's a philosopher. For him, this was a propositional logic. He doesn't ask about the connection to first order logic. And he dies in late 50s sometime, maybe 58. Just as the other line of work is taking off, he dies. And that's it. But mainly philosophers and some logicians are starting to study this logic, including famous logician, computer scientist, Dana Scott, studies linear temporal logic. And they say, what is the connection between this temporal logic and the logic that we are familiar with? And in particular, it's easy to see you can embed LTL in first order logic. What about the other direction? And the answer is no, you cannot go in the other direction. First order logic is more expressive than this LTL. But this is in 1968, Hans Kamp does a PhD thesis, and it seemed to him it's not very far. And he shows that you can extend it a little bit by adding another temporal connective, which is a binary temporal connective. Okay? And the binary temporal connective is called the until. And the idea is that P until Q is true. Now, here is a trace. If at some point Q will be true, and until that point, P will be true at any point until then. So it's a little bit of a combination of the eventually and the always, right? Something is eventually true, and always until that point, something else must be true. Okay? And notice that this has a different flavor. It's a binary connective. It connects two formulas. And this is really, today when we talk about LTL, this is it. It includes also the until. And when you add this, then you get these two logic have the same expressive power. And the concept here, I will not go into the model. The concept of expressive power is a bit subtle. There are various ways to define exactly the expressive power. And so this was first proved by Kamp, and then it was reproved in computer science in a somewhat stronger way by Gabay, Pnoeli, Shelach, and Stavi much later, in 1980. So this is what emerges, that in some sense, that the philosophical development is really equivalent to the classical development. And in particular, one consequence is this is weaker than MSO. So LTL is weaker than MSO, and that means that LTL cannot, what did we say first order logic cannot do? Count. That means LTL cannot count. And this became a theme of research that I will not get into, I just want to mention it, that when we talk about hardware, counting is a fairly basic activity. And so in some sense, LTL is really as a logic for reasoning about computer system is too weak. It cannot do something very basic. It cannot talk about counting. It cannot talk about all even moments, things like that. We have many protocols where we need to alternate a mid protocol. There are many things that we need to talk about counting. So LTL as a logic is somewhat too weak. Nevertheless, it has been proving immensely successful logic. Now, some people looked at this and says, wait a minute, it's equivalent to first order logic, so it's not interesting. Why do we need another logic? Why can't we do everything that we have done with the first order logic and will be okay? Now, remember I told you that Stockmeyer proved lower bounds for MSO. Actually, he proved lower bounds for first order logic already. So the non-elementary bounds apply equally well to first order logic. Now, what would it tell us about MSO? Here's the interesting thing. This direction of the translation is linear blow-up. It's just very easy to basically take all these clauses and write in first order logic. The other direction is non-elementary. That means that we really have to, if we go back and look at the verification question, if we look at the verification question relative to LTL, it might give us a very different answer than the verification question relative to first order logic. If we do the verification as a language containment for first order logic, we know it's going to be non-elementary. What about LTL? So we saw that the verification question was, and now we can, because we use logic, we can say given a transducer, does it satisfy formula phi? And what does that mean? That we want, this means that the language of the transducer must be contained in models of phi, right? Every behavior should satisfy phi. And again, now we can look at what is the complexity of this. And it turned out that if this was first order logic, this would be non-elementary. But now, by using LTL, it goes down from non-elementary to p-space. And it's p-space complete. But if you look more carefully, again, in time complexity, it's the size of t and 2 to the size of the formula. So it is not only linear in the size of the big thing, but it also fixed parameter tractable. And so the thing they're going to do next is to try to explain why is it that LTL, that is really have the same expressive power as first order logic, is nevertheless so much more tractable computationally. Now typically in computer science, people say, oh, this is a hard problem. It is p-space complete. But we started from non-elementary. We're delighted to have p-space complete problems. Okay? Everything is relative to where you started. So how now, and one of the questions, what does it tell us? So people say, well, it means that your formulas are much, much, much larger. But here's the interesting thing. First order logic is not a natural way to talk about time. In fact, when you go to say, when Prior invented temporal logic, what he was trying to do? He was trying to capture how people talk about time. Okay? So in some sense, the LTL is closer to the way human thinks and express themselves about time. And that's one reason why this logic became immensely popular. I don't know, somebody should check how many papers. The paper, Punoli, it's a 77 paper, and I don't know how many thousands of citations it has by now. And Punoli received the Turing Award essentially for this contribution. And here is actually a beautiful story I heard from him, how he discovered temporal logic. So he started in the mid-70s to think about people before that when they did verification, they thought, you have a program, it gets an input, it computes, it gets an output, and we need to reason about the input-output relationship. And anybody has taken any course like in Hoare logic? Anybody has seen any Hoare logic? That's what it's always about, the relationship between input and output. And Noel in the mid-70s realized that there are some classes of programming for which there is no clear output, but it's more about interaction. And it's about infinite behavior. And he was looking for a logic to talk about these kind of things. And he tried first of the logic, and it comes with some baggage that he realized. And he gave a talk about it at Penn. And somebody, Saul Goren, told him after the talk, you should look at the ontic logic. Anybody knows what is the ontic logic? What is the ontic logic? Yeah, it's the logic of permissions and obligation. What you're permitted to do, what you're obligated to do. So this is the ontic logic. So he said, okay, he goes to the library and he pulls out some book on the ontic logic and starts reading it. And he said, this has nothing to do with what I'm interested in. And he closes the book. And as he closes the book, there is very often on the back cover of the book other books by the same publisher. And there is other book by the same publisher. There is a book about temporal logic. And he just reads the blurb on the back of the book on the ontic logic. And he says, oh, this sounds interesting. So he goes to the shelf and he pulls the other book about temporal logic. And he starts reading the book and he says, ah, this is exactly what I need. So this is how he discovered temporal logic. It was what we call serendipity. So what is so temporal logic, as I said, has been immensely successful. Today there are industrial languages that are based essentially on temporal logic. So what is the reason for this success? So this is the approach that has been advocated also by philosophers. Probably the most prominent of this is Hintika. And this is called game theoretic semantics for logic. So suppose you're giving a sentence. So given a sentence, you want to know whether you're given a structure A, and you want to know does it satisfy some sentence phi. You can think of it as a game. And very often people say it's a game between one player, we call her Eloise, and other one is Abelard. Okay? That's a reference to some medieval love story with very sad ending. But the E and the A, people decided to do it, Eloise and Abelard. Why E and A? The two quantifiers. So you can think when there is an existential statement, Eloise is trying to show that this is true. And the opponent is Abelard. So you can think of it as when it's an E, Eloise moves. When it's Abelard, when it's A, Abelard move. Let's assume that the formula is a negation normal form. It simplifies things. So you push all negation to the leaves. So when it's a disjunction, who's going to move? To show the disjunction is true, you have to show that one of the disjunctions is true, and Eloise will choose which one. And with a conjunction, both will have to be true, so that's where you give the opponent choose which one to follow. So you kind of do the game, and you decompose the structure. You compose the formula, you do it inductively. So this goes back again to the 50s, I think, when people came up with this idea that this is a game. What is the problem for us with the game? If we want to translate into automaton, this game has big operation. When exists a point, it's a global thing. There is some point, somewhere on the world there is a point. Automaton don't deal very well with such global things. What do automata? Automata are very short-term thinkers, right? What's happening today? What is the input? What state will I be in tomorrow? This is it. Automata do not have big vision for the future. They're not visionary. They're all about execution. Okay? So when you define the game for first-order logic, it's not a good game for automata. But let's try to define a game for LTL. And again, we have the proponent and the opponent. Okay? Eloise is the proponent, and you have the opponent, or the protagonist and the antagonist. So we're trying to prove that tau satisfies some some formula. And again, we can assume that the formula is a negation normal form. And just for simplicity, let's assume I don't deal with the until here. Let's just not deal with the until. Just deal with G's and F's, the formula negation normal form. So we deal with negation only at the very end, so it's not a problem for us. So now that means if it's a disjunction, we have to choose one of the two sub-formula. Who's going to choose? The protagonist, okay? The proponent. If it's a conjunction, it's the antagonist. If we see x theta, we have to move the pointer to the next point in time. Doesn't matter. This is deterministic, in fact. There's no matter of choice. Just move it to the next thing. Now, let's look at phi theta. Now you're looking at phi theta, you're trying to show that phi theta is true. So now, the protagonist has to make a choice. And the choice is, I'm going to show you that theta is true here. I'm choosing to show that theta is true here. And then the game will continue. So you stay here, and you go to theta. This is one choice. The other choice to say, you know what? Mañana. Not today. I don't feel like today like doing this. Let's postpone it to the next point in time. So we were maybe at point I trying to do. Here we were at point I. Here we're at point I. Here we go to point I plus 1. And again, we try to show that phi theta will be true. And the dual will be for G. G will be, it's the opponent will choose, show me that if I said G theta, show me that theta is true today, or show me that G theta is true, going to be true tomorrow. Of course, the mañana strategy has a little problem. What is the problem with the mañana strategy? Can't keep doing it forever, right? I will pay you tomorrow, I'll pay you tomorrow, I'll pay you tomorrow. But you said it yesterday. Yes, it's true, but I mean it, okay? Come tomorrow. You told us, who told us the story about the exam? Was you? The student who keeps saying, I'll come again? Maybe it's here, maybe the student is here. So we have to add additional rule. So we have to have an additional rule. And the additional rule would say, you are not allowed to postpone forever. Okay? So this is now we're talking about infinite games, but with certain rules. And the certain thing, the certain infinite, if you the way we said it, if you postpone forever, you lose. Okay? This is what happens. If you postpone, for the proponent cannot postpone forever. Now I said, oh, look, the nice thing about it is this is much closer to automata now, because it's just very local thing. I care about what happened today and what's going to happen tomorrow. I have to think somehow about infinite, what happened to infinite trans. But we have seen infinite trans before. We've seen infinite trans when we talk about Bushy automata, and we say infinite trans have to obey some conditions. The problem is for us that this is a game. It means that if you think about automaton as a game, you can think of non-deterministic automaton as a game, but what kind of a game is it? Sometimes you play a game, you only play a game, you don't have any opponent. What do we call this kind of game? People pass the time and they sit down and play a game. What do we call play game for one player? Solitaire games, right? So these are, you can think of non-deterministic automaton, it's a solitaire game. You are making all the choices, you have no opponent. But here we have two types of opponent. So we need automata that are richer. We need automata that not only have the non-determinism, which is make a choice, but also have the other type of choice. Not only existential choice, but also universal choice. And this idea of using automata with two types of choices, and you can alternate between the two types of choices. This is the theory of alternating automata, and it was started developed in the mid-70s, partly because people were influenced by now from complexity theory. Complexity theory, we have NP, which is the existential, and what do we call the universal way of doing things? Co-NP, right? We have the dual. We have NP, we have co-NP. NP it's about existential choice. And then co-NP, it's about universal choice. And then people say, why don't we have a machine model, computational model, include both type of choices? And you can do it for Turing machines, and you get alternating complexity classes, and there is beautiful theory of alternating complexity classes. For example, you get something like, right, we had P time, and we have NP time, and you take the dual, you get co-NP time. So this is about existential choice, it's about universal choice, or you combine both, and you get alternating polynomial time. And then there is a beautiful theorem that says, what is AP time? Anybody knows? P space. Okay, so you get beautiful, that if you allow both, then you P space. Then you climb up in the complexity hierarchy. And the paper was mostly about complexity theory, but then also they said, what happens if we do it for automata? So they says we know we had DFA, and then we had NFA, and NFA have the same expressive power. And we can, of course, have co-NFA, and surely they will have the same expressive power. But they say, what happens if we put both and we get AFA? And one of the questions, do we get more expressive power? The answer is no, we do not get more expressive power. On the other hand, we know that when we went from DFA to NFA, what did we did get something. What did we gain? Succinctness. You can have much smaller NFA than DFA. There is exponential blow up when you go from NFA to DFA. The same, you gain another exponential here. So AFA can be, again, one exponential more succinct than NFA, and they can be double exponential more succinct than DFA. So not expressive power, but succinctness. So let's see what are these objects. So now I have an automaton, and I'll define directly on infinite words. And the big difference is that for DFA, we have S cross sigma to S. This was for DFA, right? For NFA, we have from S cross sigma to 2 to the S. Now, what does it mean? When we had the row of SA, and it was equal to S1, S2, or S3, I really think you should go to one of these, right? It's a existential choice. So you can think of it, I can write it this way. I can write it as a disjunction. And if I were looking at co-NFA, I would look at it as a conjunction. But if I want to allow both, I should allow conjunction and disjunction. And therefore, my definition now will be S cross sigma. And here I will take, so what is this B plus S? These are positive Boolean formulas over the set of states. So you could write something like this, S1 and S2 or S3. It says, means automaton now go to S1 and go to either one of S2 or S3. So now what is a run? What does a run look like? So I start in some state, let's say S0, and I read the letter A, and I apply this, and I get a formula here, and the formula is something like this. And now I have to find some way of satisfying the formulas where the conjunction forces me to obey everything, but I have a choice about the disjunction. So here I can choose, for example, S1 and S2, or S1 and S3. And that means that here I get one positive formula, and I have to choose the set of states that will satisfy this. So, and I continue to do that, which means I get a tree. Because at every point, I get one positive Boolean formula, and I will choose a set of states that will satisfy it. Now, the branches can be infinite branches, and I will require, now we are dealing with infinite runs. Infinite runs will require that you visit infinite state infinitely often. So I will require that every branch should visit accepting sets infinitely often. Any questions about that? So you need to stretch your intuition. You're already familiar with existential choice, this non-determinism. You can easily see that the dual of this would be universal non-determinism. You choose all possibilities. Now I'm allowing you to alternate between them. So let's just give you, we'll continue more, but let's see essentially what is the overall structure, what are we going with it? We're going to go from LTL phi, and we're going to go into an automaton, and this is going to be alternating Bushy automaton. And you will see, we will talk about it tomorrow, and you'll see it's actually a fairly simple translation. But that's not, what will I do? Once I have an automaton, what do I need to do with this automaton, for example? What do I do with automata? I solve some decision problem. What is the basic decision problem that I need to solve? Non-emptiness. Now this is more complicated automaton. It's not clear how do I solve non-emptiness, right? Automaton, it alternates. How do I solve non-emptiness? So what do? We have to reduce it to something we know about. So we will take this A phi, which is alternating, and we'll translate it to some non-deterministic version of this. And I said that generally to get rid of alternation costs you another exponential. But then I think once it's non-deterministic, we know how to solve non-emptiness in linear time in the size of the automaton, and the automaton will be exponential. And the big gain that we have gained is that now we are able to go from automaton to this translation, in fact, is linear. This is exponential. So the whole thing is exponential. And the contrast with first-order logic, what was in first-order logic? Was non-elementary. So by changing our language, going from first-order logic to LTL, we get a logic that is much more amenable to this kind of transformations. And I think our time is up, right? Yeah, okay.